Hi, welcome to another edition of Ordinary Differential Equations. Today's topic is systems of linear differential equations. So I'm going to spend quite a bit of time on explaining what does this mean and a motivation before the mathematics that we are going to do. So the first item on the agenda is to understand what is meant by a system. So we are referring to systems in this section. What is meant? Well, what is meant is that we have multiple components in our presence in our experiment. Two simple examples to consider. One is a set of spring masses. For example, we have a spring, a mass, another spring, a mass, another spring. So the fact that we have two objects that are moving here it makes it a system. More than one item makes it a system. Another example is set of mixing tanks. If you have tanks of liquids connected by pipes and then we are running water between them, we are going to have a system to consider. Before we go into the mathematics of it, let me motivate the topic a bit more by showing you some demos. So here is an example of a spring mass system that is a system as opposed to a single mass. So if you had just one mass connected to a spring, you study that in your basic science classes, you learn about simple harmonic motion and such. But here the motion is quite a bit more sophisticated and rather hard to predict as to what happens next. I'll let this simulation start and try to predict for yourself as to what happens next. Here is the movement. As you notice, as if energy goes from one ball to the other one, and then the other one stops and energy comes back the first one, and it becomes a rather interesting phenomenon. Another experiment that you can actually do at home very easily is to have a string and from that attach two other pendulums, just a string and a mass. You don't even need this spring between the two of them. When you let one of these masses to start in motion, you see something interesting. Let's see if we something similar to that spring mass system that we just saw. Energy from pendulum 1 goes to pendulum 2, and you see this one kind of stops, and then again it goes back from pendulum 2 back to pendulum 1. So just get a string and two other smaller strings, attach some weights to them, get this thing supported perhaps by two chairs or something, and then watch the movement. Just make one of them move and the other one gradually starts to move because of the vibration going to it from the string up here. That is what we are after today, to study such behaviors, behavior of such systems. Now these problems are going to be a little bit more complicated than what we have in mind. Just to get started with something simpler, we go after that tank problem. I'm going to explain why is that simpler. Let me pause this thing so it does not. Okay, mathematically speaking, how do we track such system? We always have time that is just starts at the beginning of experiment. We have x representing a quantity about one of the items we are following. For example, x could be location of mass number 1. Y would be location of mass number 2. Well, these things are going to change in time. Well, when you change in time, for example, in that problem you have velocities of each of these, accelerations, and so on. For spring mass system, of course, we do have acceleration, and that's what makes the problem slightly more complicated. Then each of these masses are in interaction with their neighbors. That interaction is described by some physical law. For example, in this case, it's just F equal to ma. And then when you write that law, you get an equation. Then you focus on the next piece and you get another equation. If I had a third piece, there would be a third equation. And then of course there will be a Z also for the third item. So as many pieces, as many components you have, there are as many equations to write. And X and Y here represents all the derivatives that you need to describe the movements. So for example, in this mechanical case, you just need the velocity and acceleration that's going to do. In the tank problem, we don't have a use for acceleration. It's just the rate at which you are pumping the water in or out. So all that you are going to see in those problems is just dx dt, dy dt, representing how strong the pumps are. We don't have any use for these. Okay. Something that is going to be used throughout here is a style of writing that is going to help us handle the problem. So of course we have dt, which is a bit kind of lengthy to write. A shorthand for it is the prime, but the prime is not very useful for us in this case. So we make another notation. D of x simply refers to the derivative of this thing with respect to our underlying variable, and similarly d of y and so on. Okay, with that as our setup, let's go ahead and see how an example problem can look like here. So example, we said we go after the tank problem because it can be done in a shorter time. So we have one tank and some other tank. So two tanks, that's what makes it a system. And then perhaps we are pumping water from that tank to this tank. Perhaps we are pumping from this one back to that one. Perhaps from outside we pump some water in. Perhaps we have some drainage to take care of here. Okay, now we need to specify, we need to specify what is in these things. Well, let's keep it simple. Let's say water and salt. So it's a brine solution. And then we need to specify how strong these pumps are acting. So the pumps are going to be characterized by the flow rate. For example, so many gallons per hour or so many liters per minute or something like that. So let's just make up some numbers here. Suppose this pump here is 6 gallons per hour, and this one pumps 2 gallons per hour, and this one pumps 8 gallons per hour, and say this one pumps 6 gallons per hour, and so on. Now whatever you're pumping in, you have some control over it. Like you can pour some salt in this thing and pour it in, or perhaps keep it pure water and pour it in. However you want to do it, that's all possibilities. Now, so we are going to refer to concentration. Concentration is how many pounds of something is going to be in a gallon of the liquid that you are dealing with. So at this point, let's suppose it's a pure water. So let's 0 pounds per gallon. So I'm not adding any more salt to the situation. We need the concentration here, but we don't have any numbers because, well, that is the holy grail of the problem. What is the water that is following this way or the other way? We don't know. So let's suppose x of t, I'm just abbreviated to x, and y of t as two main characters in this problem. This is going to be amount of salt in this tank. Let's call it tank 1. This is my tank 1. and this is amount of salt again, and this is my tank 2 in tank 2. So when you're pumping this liquid out, whatever concentration is in this tank, that's what you're going to be pumping it out. And what is that? Well, we don't know, because we don't know what Y is. Now suppose the volume of liquid here, let's call it V2, and for this one let's call it V1. So the concentration coming out here is going to be Y, whatever the unit is, pounds of salt per divided by the volume. So my volume is whatever that volume is, V2. In this tank we are pumping this liquid. This liquid has a concentration of X pounds per V1 gallon. So this one is going to be, maybe I better write it in different color. So this is X over V1, and this is Y over V2. This one was 0. We intentionally set this one to be 0. How about this one? Well, this is same as that liquid there, like the concentration here and the concentration here are the same. And all these mixing problems, the assumption is that we mix the liquid quickly so that we have same kind of liquid all over the place. So the concentration of this one is also Y over V2. Now, okay, how does all of this have anything to do with differential equation? First, let's go do a simple accounting of what is the deal with the volume. Let's suppose the volume at time 0 at the beginning of an experiment, this is given as say 100 gallons. That is, at the beginning we have filled this thing all with 100 gallons. And just to keep it simple, let's say V2 also is 100 gallons. So this is 0. It just refers to what's the volume in the tank. And volume is also changing with everything else. It could be changing, it could be constant, it all depends. Now what happens to my volume? So volume, I have to figure out at time t, because these are volume at a given time t. What is that volume? Well, at the beginning I'm starting with 100 gallons. And then I'm pouring in 6 gallons per hour. So 6, how many hours will let it pass? Well, t hours, 6t, that's how much I'm pouring in. Well, I'm also pumping out, so I'm pumping out 8 gallons per hour. After t hours I have pumped out this much. And from the second tank I'm pumping back into the first tank 2 gallons per hour, and then, well, after t hours is going to be this. And this problem is adjusted so that we don't get into a complication of overflowing a tank or completely draining a tank. So if here I see it becomes 100 plus 0t, which is just 100. So that means we are keeping the volume stable. The volume is not changing. Volume of tank 2, how about what's going on there? That one we said starts at 100 gallons, and then we are losing how much? We are losing 2, so gaining 8 and losing 6. Well, then of course this one also kept at 100 gallons. So volume is a fixture, at least. So our problem is going to be substantially simpler than alternative if the volume was also changing. Well, How about the amount of salt? Is that changing? You bet it is. You are mixing these two and pouring in some fresh water, so things could easily change. To keep the problem going, we are going to assume the amount of the salt in each tank at time 0. So that's going to be our initial data. So we are going to assume like I have some salt here or some item dissolved in water, and that's going to be at time 0. Perhaps I assume that this one is 5 pounds of salt in it, and this one I'm going to assume perhaps there's 10 pounds of salt in it. Some numbers given. So in addition to the pump information, we have to give initial configuration of the tanks, how much salt is in it, and initial volume of the tanks, how much water was in it. Okay, now comes the punchline of the whole problem. The question is, how does X change? Remember, X is the amount of salt in the tank. It's going to change because you are pumping stuff in or out, and they have all sorts of concentrations. This one, you're pumping it in. It's fresh water, so you're not adding any salt into your tank. But just to make the problem general, the amount of liquid that's coming in, that is their flow rate, is 6 gallons per hour. Each gallon of it is bringing 0 pound of salt to your tank. If it was salty water, you have to take care of that. Then, salt coming in, pouring in here. So how does that one work? That is coming in at the rate of 2 gallons per hour, and it has a concentration of Y over V2. Well, Y V2 thankfully is kept at 100, so this is Y pounds per 100 gallons. That's what is coming in. This one is taken out, so I have minus at the rate of 8 gallons per hour, and the concentration that is taken out is X pounds of salt per 100 gallons of water. That's the concentration here. Now, same story for tank number 2. So let's keep these numbers in view. dy dt is what now? It's what is coming in and what's going out. Let's write well, what's going out. You're taking out here and out here. So let's write 6 gallon taken out in this pump, 2 gallons taken out on that pump. So I have 8 plus, sorry. I have 6 in one pump, 2 in the other pump. Both of them are taking water out, and concentration of outgoing is Y over V2, V2 stationary at 100. These are taken out, so I have to subtract. From tank 1, I'm pouring into tank 2, so I have, now I have 8 gallons, 8 gallons per hour, and the concentration that's coming in is X over V1, which in this case is X just over 100. Okay, I hope you redo this thing and convince yourself that that's the correct setup. Now I have dx dt. Let's write it clean mathematical style. So that is 0. Thankfully that's just 0, so we have one less headache to deal with. And now you choose to write x first or y first, but do the same thing in um, all of your equations. So this is 8 over 100 minus 8 over 100 x, and this is 2 over 100 y. In the second equation, we line up same way. So that's going to be 8 over 100x minus, this is again 8 over 100y. This is, well, what do you have? We have a system of what? Of ODEs. And then we have an initial condition, like in the first tank we had 5 pounds. In the second tank we had oh yeah, 5 and 10. So we made some assumptions. So that is the initial conditions. What saves the day is that this equation is linear, meaning like you don't have x squared and cosine of y or radical x and stuff like that. So important aspect and something that dictates our method is the fact that these things are linear. So what you see here, now let's write this thing as our new notation dx. On the right hand side you see some number times x, some other number times y, and then you have dy, some number times x, some number times y, and you have your initial condition. So that's an example of a general first order. This is a first order system of linear ODEs, linear and homogeneous. Like we don't have any numbers. You will see many different ways of solving this problem. Probably in each course that you take, there is a different approach, different favorite method of solving it. And here is one approach that we are going to have, and that's called elimination approach. So we are going to solve this problem somehow reminiscent of what we used to do in college algebra, where you might have had, say, 2x plus 3y is equal to 5 and 4x minus 7y is equal to 11 and stuff like that. You multiply that by 2 and subtract from this one and do manipulation like this to get rid of one variable in favor of the other one and approach the problem that way. So what we are going to do here is same style. So we are going to go after eliminating one variable and just focusing. So we are going to use method of elimination, and again, you might come across many other methods in different courses. And okay, now let's go ahead and attack this problem. So okay, I'm gonna work with this because these numbers are going to distract us a little bit. Just trying to keep track of who went where and plus minuses, etc. So it might be a little bit more advantageous to have these parameters, and then we are going to have a recipe that we can apply to all similar problems. So what do we do? Again, as I said, pretty much every class has one of these, and everyone has their own favorite way of approaching it. Here I will write bring everything to one side. So on the second equation, I write the x's first, just so that our order is maintained. Just as a reminder, d means differentiate. So dx simply means x prime. And ax means, well, a number times x. We can do just like how we were doing in algebra, that factor the d out and write this in this way. That's going to be more suggestive as to what to take next. And then we have d, capital D, minus little d, y equal to 0. So this is a system of equation, pretty much like what we have had in high school and such. And we can do elimination or substitution exactly like how we used to do in high school. For example, I can multiply this equation by a c and this equation by d minus a in order to cancel x. We can decide to eliminate x, or we can decide to eliminate y. If you want, you can use a substitution, like from this equation you can write y is d minus a over b times x, just like how you would have done it with numbers. And then what? Well, we can take that and substitute in the second equation. So I'll have minus cx plus d minus little d times, it's the y, I put this thing, which is d minus a over b times x equal to 0. You can clear the fractions like how you clear fractions any other equation. D minus d and d minus a, excuse me, there's a x here I'm missing, times x equal to 0. We can factor the x, so I'll have d minus little d d minus a and then minus bc, all of it times x equal to 0. So we are treating d just like a parameter. When you multiply this out, what do you get? You get d squared, d times d, d squared, dA and dd, a plus d times d. This is just a number, minus bc. Whole thing times x is equal to 0. Now let's remember what d meant. D meant differentiate. So d squared means differentiate twice. So that equation is equivalent to x double prime minus a plus d times x prime minus bc is equal to 0. I am missing something. Let me go back and make a correction. I wrote d squared, d and a times d. I am missing a times d. Sorry for that. Let me go ahead, make a correction, and so I should have written plus ad minus bc. So a times d and minus bc. Let me go ahead, make a correction here as well. Well, what does this look like? It looks like the differential equations we had a couple of lectures ago. Now, those of you who have taken your linear algebra class recognize these creatures. So let's go back to what we have here. What we have here, typically recorded as a matrix, these four numbers A, B, C, D that show up right hand side. This is sometimes referred to as a coefficient matrix. And then in that matrix, some of these two diagonals, if you remember, had a name there. It's called the trace. That's what shows up here. And the product of these two minus these two AD minus BC. Do you remember what was that one called? It was called determinant of the matrix. So the quantities that show up here are significant and they have their own names and everything. Now all that is left for us to do is we'll go ahead and solve this, but this doesn't pose any new challenge to us. We have this kind of problem solved several times before, and let's go ahead. In our problem, our A, B, C, D are these quantities, so let me write it. A was minus 800, B was, see, I forgot already, B was 2 over 100, C was minus 8 plus 8 over 100, and D was minus 8 over 100. Well, we are going to plug our numbers here and then solve our equation. So in our equation, what do we get? X double prime minus A plus D. A is 8 over 100 minus D is same times X prime plus AD. 8 times 8 is 64, and denominator is 100 squared, 10,000, minus B times C. 2 times 8 is 16, and denominator of that also 100 squared, times X equal to 0. Okay, just some numbers. This one becomes 16 over 100. Perhaps better not to simplify. And this is 48 100, yes, 100. 48 over 100 squared x equal to 0. A little bit unfamiliar numbers, but we factor it same way. What are two numbers such that the product is 48 and the sum is 16? What do? We write the characteristic equation. Remember, we had a characteristic equation to write. That is, we are searching for solutions of the exponential type, like exponential of some mt. When you put this thing in the equation, you get m squared plus 16 over 100 m plus 48 over 100 squared is equal to 0. You factor this thing, product 48, sum 16, that's 12 and 4. Denominators are like 100, or factor however you feel comfortable about that, equal to 0. So I get two roots. Luckily I get both of them real numbers, must be real numbers, and then our solution becomes what? A times exponential of one of these numbers. So I write, for example, minus 4/100 of t, and plus b exponential of minus 12 over 100 t. So I have general form of x. I still don't have my a and b. Where do they come from? They would come from the initial conditions. But before we get there, we better clarify the situation for y. Now, just the same way I canceled the y into these equations, I could have canceled the x's and end up with exactly same equation for y, meaning x and y are both of them solution of the same differential equation. But instead of duplicating our effort in that way, we might as well pay attention to this. When we were doing the substitution, we specified what is y in terms of x. We solve this equation, we got that equation, so we might as well make use of it and get our y straight, because we have the x already. We have the x, and all we have to do is to apply that. We had previously y is equal to d minus a over b times x. Is that right? D minus a over b times x. What we have to do is to take this thing and multiply by that. So what is d? These are just differentiation operation. Who is a? A at minus 8 over 100, so that's going to be minus 8 over 100, and b was 2 over 100. I might as well multiply numerator and denominator by 100 to clean up a bit. Divide by 2, perhaps, or leave it as it is, either way. This is all of that multiplied by x. I forgot to write my x. All of this multiplied by x. So who is x? X, we had it here. I have to multiply that by x. Let me do piece by piece. Let's take this and multiply it by 50d plus 4. So I have 50d plus 4. Let's multiply by this component first. A exponential of minus 4 over 100t. All we are doing here really getting used to what d means. D means differentiation. So 50 times a, and then derivative of this. Well, what's the derivative of that? The exponent comes down times exponential of minus 4 over 100t. How about 4? Well, that's just ordinary multiplication of a number. 4a exponential of minus 4 over 100t. So really, it's just learning to play this game with the letter d, d meaning differentiation. Well, I can clean this up. 50 times minus 4 minus 200 over 100, that's minus 2, and then plus 4. Minus 2 plus 4 is going to be 2 exponential of a to the power of minus 400t. So I took this, multiplied by this piece. Now I multiplied also by the second piece. So you may perhaps you want to go ahead and do this yourself. 50d plus 4 times this one. So that is going to be b exponential of minus 12 over 100t. So that's going to be 50b times, no, the derivative of that is going to be minus 12 over 100 exponential of minus 1200 of t, and then 4b times the same. Well, 50 times minus 12, that's minus 600, divided by that minus 6 plus 4, takes a total of minus 2b exponential of minus 4 over 100t. So, we can put these things together. Y then, multiplying this by x, is made out of these two components. I have 2a exponential of minus 4 over 100t, and then minus 2b exponential of minus 4 over 100t. So that took a while, but we have x, and then we have y. These are the solutions for that system. There are two constants in this problem. Where do the constants come from? Well, each of these problems have initial conditions. By taking that into account, I'll find A and B. So what was our initial condition? Our initial condition was this tank starts with 5 pounds, that tank starts with 10 pounds. So let's keep that in mind. Okay, let's put our solutions together. I have x was a exponential of minus 400t plus b exponential of minus 1200t. Y turned out to be 2a exponential of that. The minus 2b exponential of minus 12 over 100 t. Well, what about a and b? Well, at time 0, x0 becomes a plus b, and y0 becomes 2a minus 2b. Our problem specifies the initial amount for these things. I guess we specified 5 or 10 or some number. So you end up solving a system. This will be easy. Double that and add to this, get 4a over 20. Our a becomes 5 accidentally, our b becomes 0. Just pure coincidence. So x becomes 5x exponential of minus 400 t, and y becomes double of that, 10. So in this case, our final solution became extremely simple. Well, it doesn't have to be. It can have two components in it. In all cases, x and y have to be positive at the very end, so it's not completely arbitrary either. Okay, that is perhaps one solution for today. In order to avoid having a very long lecture, let me postpone the second differential equation we were going to do for next lecture. So maybe until that time you want to solve this thing yourself. Now suppose we had 3 tanks, and our equation turned out to be the following. Never mind what the background of the problem is. So we can have x, y, and z, their derivatives given in terms of x and y and z. These are all linear functions. That's what make our approach work. If you had to log y squared, cosine of x, radical z, and stuff like that, our approach will completely collapse. It's only good for the linear equation. So until next lecture, where hopefully you find x, y, z. The only new challenge, well, there's going to be some challenges, is when we want to solve our system. Well, our system gets bigger, and there are more components to it, and the problem becomes a bit lengthy in that regard. And perhaps we'll talk about using some apps for doing this. So again, what was the discussion today? We talked about a system. What is it that makes a system? It's having multiple components. We write a physical law that relates each component to the other ones, and each of them gives us a differential equation. And then when we put all these equations together, we have a system of equations. So the multiplicity of equations comes from multiple components of the system. Derivatives come in because in all physical laws we have some rate of change. In Newton's case, it's very obvious. You have acceleration is a second derivative, but in all sort of even rather trivial cases like this mixing tank problem, you still have a derivative indicating how something changes. Okay, until next time, good luck and God bless.